properly. Good evening to everyone. My name is Kat. I am the Physics Access Officer at Oxford University, and welcome to the fourth webinar of the Preparing for the CAT-PAT course 2024. My name is Kat. As I said, my pronouns are she and her, and I run most of our programs for secondary school students, including all of our stuff that supports people like you who are interested in applying to study physics and other subjects here in Oxford. The session is being recorded as well as being live streamed on YouTube, and it will be made available to you tomorrow. Quick reminder of the housekeeping rules for those of you joining us on Zoom. You will be able to use the Q&A for any questions that you would like to be addressed. It's currently switched on and ready. You can also access the chat at various points this evening, but please keep it polite, keep it kind. Don't share personal details or information such as phone numbers or email addresses. And very important, don't use it for any questions that you want us to answer, because otherwise it may get lost. If at any point this evening you are feeling unsafe or concerned about anyone, you can contact our safeguarding lead on safeguarding@physics.ox.ac.uk. I'm going to switch off your access to the chat for this first section of today and introduce both our PAT test and our course. Before we start with our session this evening, I wanted to give a quick introduction to the course and the PAT. As I've said, I won't take questions in this section, but don't worry, we have a webinar in September just for PAT logistics and all of your questions. First things first, the PAT is the physics admissions test, and it is the required test for physics and philosophy, engineering, and materials science. Your result on PAT forms part of the information which admissions tutors use to decide who to shortlist for interview. In order to sit the PAT, you will register yourself as a candidate. Your school will not arrange this for you. The PAT this year will be on screen and entirely multiple choice. There will be 40 questions with a total of 100 marks. We've worked hard to make sure that we can gain as much information as possible from the format. So as you can tell from that mark distribution, the answers are not simply 1 mark or 0 marks. The syllabus is unchanged and the questions will be really similar in style to previous years. The online test will include a built-in on-screen calculator, which looks exactly like a regular calculator and works in just the same way. You'll do your working in an erasable answer booklet, which cannot be removed from the exam centre. That's the PAT. The PAT course is exactly what we are on now. This webinar is part of the PAT preparation course, and I run this course on behalf of all subjects who require the PAT. The course consists of 8 webinars, along with problem sets and summer assignments that we hope will provide you with all the information you need to take the PAT, to help you prepare for the PAT, and to feel confident going into interviews if you're shortlisted. The timetable that you can see on screen at the moment is part of the timetable which is at the bottom of every PAT email that I send out. And I always highlight in yellow where we are so that you can follow your progress. In each session, I'll make sure I fill you in on any updates or news, especially as we get closer to any of those key dates. Today, we've got our second solutions webinar. You see us highlighted in yellow. And all of the information about the course, all of the course materials are on this page here. And I share this link in every email. The introduction to physics problem solving, which I've circled, is always at the top of that page. It has some general hints and tips, which we went through in our first webinar, but also lots more details. It's well worth a look. And then underneath, under recordings and other materials, every week I will update this and you have everything that you need. So you've got problems used, recordings of sessions, problems to solve for the next webinar, all really clearly labeled so that you can find everything to help you navigate the preparing for the PAT course. So that's the basics of the test, the basics of the course. Finally, a quick reminder that all of the information both you and your school need can be found at the page on screen just now. Again, I share this link every week, so don't worry about making sure you've got it copied down. It's the most up-to-date page. It's the one that you can check first for any information that you need. It's also got a really useful FAQ page. Some key facts for you as we come into week 4. All candidates will sit their tests at Pearson test centres this year. There are venues in almost every country around the world, and when you register, you will be able to select a centre which is most convenient for you. It doesn't need to be the one closest to your home, for example. For some people, you might involve some travel, but hopefully not too much. This arrangement is a little bit different to previous years, but really importantly, it's the same as the setup for tests like the LNAT, the BMAT, and the Cambridge admissions tests this year. So Pearson are really experienced at running these tests. Registration for the PAT will open on the 15th of August and will be open until the 4th of October. When you register, you can select a test centre, as I've already said, and you can also apply for access arrangements such as extra time or breaks. It is free to register for the PAT. The PAT is being held on the 28th of October. We are aware of some clashes, and I'm meeting with our admissions team the next week to get some more information about the procedure for that. And I'll be able to update you when we come back in September. I mentioned our test format, and although it's a new test format, it's not that big a change. As I've said, questions are really similar. Syllabus is unchanged. But even though it's not a big change, we don't want anyone feeling anxious. So you can access a trial version of the test already, practice test with a calculator, and you can see what the test looks like in advance. You can practice using the calculator. You can even have it open and use the calculator for other homework so that you get all the practice that you need. That is my quick PAT introduction and update. I hope it was helpful. I may have time to take questions at the end, but if not, don't worry. As I've said before, we have a whole session in September where we're just going to talk about multiple choice technique, what the PAT's going to look like, and making sure that all of your questions get answered. For now, though, it is time for me to introduce our lovely students who are going to be leading you through the rest of tonight's session. So I believe first up, we have the lovely Nina, who is a PhD student, as well as having done our undergraduate degree. But I'm not going to introduce her. Nina, over to you.
Hi, thank you, Kat. Hi, everyone. My name is Nina. I'm at UNIF. I did physics as undergrad, and now I'm doing my PhD again in Oxford in particle physics. So yeah, I've been doing outreach for the past 4 years. So hi to the next generation of people who will be struggling with the PAT. It'll be fine, I promise.
It will be.
Yeah. Let me share my screen.
Lovely. What I'll do, Nina, is just while you were sorting that out, I've reopened the chat. So please feel free to talk about your own solutions. Q&A is open. So if you have any questions for Nina about her work as we go through, please pop those in the Q&A. And I will also share in the chat the link to today's problems for anyone who has missed them. Is there anything else you would like from me, Nina?
No, that's okay. Thank you.
Perfect. In that case, I'm going to disappear into the background and do all those things.
Yeah, if you can just tell me if you see my screen properly.
I can.
Yeah, okay, good. Thank you. I'll be looking at the Q&A at the end of each problem, and I'll give like a minute for you to type out questions. So starting with the first question, we are dealing with optics this time. So the first question is pretty straightforward. They say, consider the diagram in figure 1, indicate clearly the position and nature of the image formed by the mirror, and then draw rays corresponding to light coming from the open circle and mark any relevant angles. So with this sort of problem, read through it word by word and do everything they ask you to, not just draw the rays, not just look at the diagram, but make sure that you're covering every point. And when you have a diagram, usually it's a good idea or a very, very good idea to redraw the diagram, even if you don't have to draw something on it. So you have our mirror, you have your object with the white point. I'm just going to look at the chat in case something's wrong. No. Okay. And then you have your observer. Oops. Then you have your observer. So the first thing they ask you is to draw a ray diagram. So from your object, light rays are going out in all directions. The ones which you're interested in are the ones which get reflected through the mirror, right? So you would have a ray which goes down, gets to the mirror, always draw your perpendicular to the mirror, because in this case, you're working with a flat mirror. And then the ray goes up to the eye. You don't need rulers necessarily, especially in terms of time. It can just be a sketch. Always mark your angles. In this case, they say it explicitly, but in general, so this is incident theta, this is reflected theta, and flat mirror means that those two angles are equal. Make sure you point that out. So they want you to build the image. An image is built in a mirror through the extension of the rays you see. So the ray that gets to the observer, you extend it back. And then a second ray you can use always from the object perpendicular to the mirror, because this is a ray that goes down and then reflects back into the object. So where those two rays cross, this is your image, and this would be the whole object if you do the same thing for each point of it. So this is your ray diagram. You have, this is again theta reflected or refracted. So go back to the question. Consider the diagram, indicate clearly the position and nature of the image. So position, definitely write down that it's equal distance. So I'm not going to write it out, but equal distance, so those two distances basically are the same, is what I'm trying to say. And nature, there are always two things we should mention about an image, whether it's inverted or straight. So in this case, it's inverted. Yeah, it's not flipped. And whether it's virtual or real. In this case, it's virtual. And the definition of this is that it's formed by the extension of rays. A real image is formed by actual rays, and you can put a screen on which you can actually physically see your image. In this case, you can't because you have a mirror there, right? Which means it's a virtual image. Also worth mentioning that it's same size, so you don't get any magnification. Yeah, I think this is all that I would cover in this problem. And the problems are multiple choice, but in your workbook, you will have a place to draw diagrams, to explain things, and you don't just get a point for a right or wrong answer. So make sure you write down the answers to all like sub questions and explain your thinking and explain your working properly, okay? Yeah, I'm looking again at the question because I have been burnt multiple times, but not by not reading the question properly. So please don't miss any parts. But I think that's all right for this question. Q&A, how can we learn more about describing reflections? I've never even touched on this in school. I think more or less this covers it, literally just saying whether it's inverted or flipped, inverted or what's the word? Straight up. Whatever word you write, they're gonna understand you. If Kat, you remember the actual term, you can put it in the comments. Then whether it's virtual or real, and comment on the size. I think those three things cover your bases. But it's a bit early. You'll start doing past papers for the PAT, and you see enough questions to start building up what the expectation is. So don't worry about it too much. Can you please explain virtual again? Yes. So in this case, how you build your image is so you have your actual physical ray. So those are photons traveling from your point. Whoops. Photons traveling from your point to the mirror, getting reflected and going into your eye. This is the mirror, right? It's a physical solid object. So there's nothing actually going in it. But how you see the image is by the extension of the rays, the projection that goes into it. Same goes for this ray. So this is a ray here, which starts from the object, goes down to the mirror, and then gets reflected back into the object. And you just get the extension. So if you build an image as from the extensions of rays, you get a virtual image. In contrast, if you have, what would be a case? So you have an object, you have I think if you have this sort of mirror, oh my God, I'm trying to remember. And you have an observer here, you get a ray which is reflected from this mirror, and then another ray which is reflected from the mirror like this. And those two rays meet. See what I mean? And in this case, those are actual rays. Those are actual photons traveling and getting reflected from the mirror and going back. And the image you form here is now real, because if you put a screen here, so a detector, the CCD or whatever, camera, actual photons will land on this camera and you'll be able to detect your image. And this means that it's a real image. Okay, I hope this makes it clear. Why is it inverted? Because how do you define this? I go by, if you just look at the ray diagram, in one case your object, let me switch colors. In one case your object looks like this, pointing up. In another, in the image, it points down, and you can determine this by, instead of taking this point, you can take the top of the arrow. You go like this, and go down here. So the top of the arrow from the top goes to the bottom, right? It won't go here. So this is why it's inverted. Okay. Whereas in this case, if we also image the bottom of our object, it will go somewhere here, here, and so the bottom will be down here, the top, as before, will be here, so the image will be straight. Since the path is multiple choice, we aren't going to be asked to draw diagrams, right? Kat, can you confirm whether
Yes.
Yes?
Yeah, we had a similar question about working as well, where somebody said, I won't be marked on my working, so I don't need to do it. So I'd say, in the sense that we're not going to mark your diagram or your working, no, it's not necessary. However, you're still going to need to solve these problems, and you're still going to need to solve these problems as you work it out. So you probably will find yourself drawing diagrams and showing your working just in the course of doing the PAT. The only thing that is different is you'll be selecting an answer at the end. So whether that is which diagram is correct or which description is correct, the problem solving process is exactly the same. And I don't know about you, Nina. I struggle to see how I would do that without a diagram.
Yes, yeah,
Yeah.
definitely. The other thing is successfully passing the PAT means going to an interview. And the interview will
Yeah.
1000% involve you showing and explaining your work.
Yeah.
Um,
Is that okay?
yeah.
Great.
Okay. I think that covers this problem. But yeah, the main thing here was, what is an inverted image? What is a virtual image? How do we build those, and so on. Obviously, if you have questions on previous problems, drop them in the Q&A and I'll go back. Okay, so question 2 says a parallel-sided slab of medium B and the refractive index is sandwiched between two slabs of medium A. Okay, a beam of light passes from A through B into A. If the beam is incident on B at some angle, what is the angle to the normal after it has left B? Okay, so again, it's one of those things where you kind of do need a diagram because you need to see what's happening. So yeah. So you have a medium B, which is sandwiched between two different mediums A. And each of them has a refractive index, which is given to you. A beam of light passes from A through B if the beam is incident on B at an angle theta to the normal. Again, I'm reading through the questions just to show how I would decipher the information and not miss anything. Going back, okay. So we have our normal, and we know that our ray is incident at angle theta. Then what happens is that this gets refracted, goes through B, lands on the border between B and A, it gets refracted again, and gets to the end of A. And they're asking, what is the angle to the normal of the light beam in A after it has left B? So they're asking for this angle. Again, in the beginning, make sure you know what you have as information, in this case, the refractive indices and this angle, and what you're looking for at the end, which let's call it angle theta A. Yeah. So first thing to note is that after refraction, you will get some angle B, and because those two lines, the perpendiculars, are parallel to each other, this will also be angle B. So again, if you're in an interview or you're writing this out, do you mention the alternate angle rule or explain it in some way? And then, as per usual, when you have any sort of refraction and you need connections between angles, you definitely go to Snell's law. And Snell's law says that the refraction angle in this region times the sine of this angle will equal to the refraction coefficient in this region times the sine of this angle. So this is for this boundary. And then you have more information. Always write out all the information you have, especially if you're unsure how to continue with a problem. Even if you just find equations which look like you could do maths based off of them, it's always helpful. And especially for multiple choice, you don't have to actually understand. If you find maths which works and gives you an answer, go for it. The exam is not the right time to decipher everything and make sure you do things properly, right? But for now, you do want to do things properly. Anyway, you have two equations. You have this angle given in your problem, and you're looking for this angle. Obviously, you equate those two, and what you get is that sine theta equals sine theta A. In principle, be careful with equations with trig functions, because this does not automatically mean that theta equals theta A, because you have the sine, cosine. So this angle would have the same sign as this angle, right? So be careful with that. But in this case, we're working with angles which are less than 45 degrees, which allows you to say this. And so your answer is it multiple choice in this case? Yeah, okay, so B, answer B. Yeah, label your angles and indices and everything. In principle, if you're asked for written solutions, draw a diagram, definitely. I think these are all my notes on this question. Do you have any questions on this? How do you know which material is denser, and does it matter? In this case, it does not matter, because when you draw the diagram, for example, it's just a diagram. You don't need to take into account whether theta is bigger than theta B or whatever. The maths would be the same, because, yeah, we don't use one of the signs, for example, being bigger than the other. Can you explain unit circle for sine? Yes. So yeah, let's work with this unit circle. Sines and cosines, because sine squared plus cosine squared equals 1, right? Because of this, we can always draw a unit circle with a radius 1. And its radius, let me draw this bigger. So if you have a radius of 1, you can always have a vertical projection and a horizontal projection of this radius. And because of Pythagoras' theorem, because this is a right angle triangle, x squared plus y squared has to equal 1. So what we do, just as a useful visualization tool, is that we say, okay, x is our sine, y is our cosine. Oops. And our vector defines our angle. So if you look at the unit circle, the projection of our vector, which is formed by our angle, can give us the sine of this angle, which is the value of this axis, and the cosine of this angle, which is the value of this axis. So if you have an angle of 0, which is just our vector being here, so theta is 0, we know that it will have, this is the other way around. So this is sine, this is cosine. I do apologize, but it's how life works. So if you have a vector which is just on the line here, so theta is 0, you will have a 0 vertical projection, which means that sine of 0 is 0, and you have a horizontal projection of 1, which means that sine of 0 is 1, right? And so when you move around this vector, you get the corresponding projection. Yeah, and my point was that this angle and this angle will have the same projection along the sine axis. So you kind of have to be careful. They are not necessarily the same, but because we're working in just this quadrant, that's fine. Okay. Could you go over again the part where you explained why not always? Yeah, okay, so this is what I meant. Just when you're doing maths, sometimes this is the trick of the question, right? Some questions have a little trick for you to, yeah, get it wrong. This angle, theta, and this angle, theta, will have the same vertical projection, so the same sine, but they're not the same angle. Why and how did you remove NB and NA? So I looked at those two equations. Let's change color again. I looked at those two equations and I saw that this term is equal to this term because they are both in here and we have the same theta B because it's an alternate angle. And so I equated this to this. And then got rid of the NA. Yeah, maybe I moved a little bit too quick. Okay. Okay, there's a animation of the unit circle in the comments. Okay, cool.
Just to save you trying to plot every single point, Nina, I could see where you were going with it, and I was like, "It's a graph of that. I'll just post it."
Yeah. But yeah. Cool. Okay, cool. Again, if you have questions on previous problems, I will go back afterwards, so don't worry to post them. But some blue. And go to question 3. Okay, so a parallel beam of monochromatic light initially traveling in a direction above the horizontal enters a region of atmosphere in which the refractive index increases steadily with height. Which of the graphs will represent the path of the beam? So a parallel beam of monochromatic light basically means that the beam of light, all of the photons in it are going like this, parallel to each other. It's not like spread out. And then monochromatic means that it all has the same wavelength. So it doesn't refract in different ways. So each of those little rays, if they get refracted, will get refracted at the same angle and it will be still parallel. So this is just for you to not think about complicated stuff. Initially traveling in a direction above the horizontal, which is a very weird way to put it, but what they mean is that if you have the horizontal, initially the rays traveling like this, but you can see this from the diagrams. Reaches atmosphere where the refractive index increases steadily with height. So say the atmosphere starts here. We know that our beam will get refracted in some way. So they're asking how. When you have a change, even a gradual change, a very useful thing you can do is make it into a discrete change. So take the whole atmosphere and separate it into layers. So this is our atmosphere, these are our layers, and we know that it goes from some refractive index N1 to N2, which is larger, and then to N3, which is even larger. This is what they say, right? Increases steadily with height. Okay. So what we know is that our beam comes like this. So they ask how will it change afterwards. One way to do this is Snell's law. Again, when you need a relation between angles, you always go to Snell's law. So we know that N1, or okay, this is N, the place from where our beam comes from. Oops. So N times this initial angle theta equals N1, which we're in this region. I'm not, intentionally not drawing it because we don't know the size of the angle. In this case, it does matter because this is the whole question. But it will be some angle N1, theta 1. We know that N is smaller than N1. And in order for this equation to hold, we would need sine theta to be bigger than sine theta 1. Or a more obvious way to do it is this. You can rewrite as N over N1 equals sine theta 1 over sine theta, if you divide both sides, right? So we know that this, because N is smaller than N1 is smaller than 1, which means that this should be smaller than 1. Therefore, theta 1 is smaller than theta, using, again, the fact that they're both smaller than 45 degrees. Okay, so what we learn from this is that our ray will go closer. Whoops. Our ray will go closer to the vertical after it goes through, right? And then the same applies to all of the above. So it comes here and goes even closer to the vertical, and so on. And the key thing here is that those little regions can be infinitely small. So there are some deltas in terms of thickness. And this is how you build up your atmosphere. So an infinite amount of infinitely small layers means that your ray will start curving up. In the answers, this could correspond to B, potentially E, but yeah, I'm not sure how a ray would start going backwards. As you can see, because of this equality, this sign can never go negative. So the refraction can't go this way. So you know it's B. And also you know it's smooth. It's a smooth line because they say that the index increases steadily. Okay. A way I remember those things, which will make it quicker if I get my point across. If you have a ray coming from something, from a medium into a denser medium, if you imagine a car going from a road into sand, which is a denser medium, once this wheel reaches here, it will start going slow, whereas this wheel will still go fast because the sand is denser than the asphalt or whatever. And so the car will start turning this way. And once it's in the other medium, it will be tilted this way. So the ray curves towards the perpendicular. It's just a dumb way to not go through all of this when you have multiple choice. So if you like this, use it. Just look in the Q&A. So far, nothing.
Yeah, I think this one has obviously been confidently received, Nina. Well done.
Good. Okay, let's set up a new page.
And I like the little bit about multiple choice technique that you had at the end there. We're going to be covering that on September the 11th, I think.
Yeah, because things
Yeah.
do seem different now.
Yeah, absolutely.
Okay, question 4. A narrow beam of light is incident normally upon a thin slit. The light that passes through is spread out by diffraction. The thin slit is then immersed in a container of water, and the same thing happens. So they're asking whether the spread of diffraction of the beam of light in water will be the same, different, more or less, whatever, compared to air. So what's happening is you have a thin slit, you have a beam, this beam spreads out. In one case, this is happening in air, in one case, this is happening in water. So there's 2 key things to consider here. One thing is a fundamental rule which you should remember for all of the problems you might encounter, is that the speed of light is equal to the frequency of light times the wavelength of the light. And very importantly, the frequency of the light is constant. It depends on the source. Once the light is out of its source, once it's generated, it does not change frequency. It can go through water, through oil, through air, through vacuum, whatever. The frequency is a constant characteristic of your wave, which is defined by the source of the wave. Please remember this. So, we know that in a medium, the speed of light is expressed like this compared to the speed of light in vacuum, which is c. So speed of light in vacuum divided by the refractive index of the medium. And we know in water is bigger than in air, right? Which means that in our case, V goes down. The speed of water goes down when you submerge your slit into water. For this whole equation to hold, this means that the wavelength of your light also goes down. Okay, and in fact, you can write the new wavelength as the wavelength over n, the incident wavelength or whatever in air. Okay, so this is the one thing. The other thing, which you could remember, you could derive, you could just have as intuition, is that if you have a diffraction pattern, the angular position of the minima, and I will explain this in more detail if people haven't derived this yet, is given by this, where d is the size of your slit. So again, this is something you derive like once, or maybe there are problems with it, but you might encounter it, so it's nice to know. So when you have a diffraction pattern, you know how if you have a screen here, it will be like a wave. So you have maxima and minima. And if you take the central that goes through the center of the diffraction pattern, the position of the first minimum, this is theta, the angular position, would equal the wavelength of your light over 2 times the size of your slit. Anyway, this is important because with our wavelength going down, this means that the first position of the minimum will be at a smaller angle. So if you previously had a minimum here, now you'd have a minimum somewhere here, right? Which means that the whole diffraction pattern will basically shrink. And I believe this is one of your answers. Fraction pattern will, yeah, less spread out than in air. Answer C. Something I guess useful you can just remember is that diffraction is more effective on shorter wavelengths. So the shorter the wavelength, the more it gets diffracted. And especially for multiple choice, if you just know that, that's fine. Okay. quickly looking through questions. What was the answer for 3? Was it B or E? Let me just go quickly back. Yeah, so the answer for 3 was B, because you always have a positive angle, so you can't go backwards on the perpendicular. So the answer to 3 is B. And then are we justified using equation n times lambda equals d times okay, let me see what you mean. Are we justified in using this equation, n times lambda equals d times sine over? Yes, yeah. So this is for maxima, I think. Like I'm just a bit confused by the factor of 2, but if you do the derivation, like depends on exactly how you define the size of the slit. So you could be working with d over 2. The numerical factor doesn't matter. And n is, in your case, the order of your peak. So this is not the refractive index. This is 1, 2, 3, and so on. So in this case, I'm looking at the first minimum, but this could be the second minimum, third minimum, and so on. So yeah, this is basically the same equation. So if you remember one of these, that's fine. Could you explain how we derived? How is that equation derived? Could you quickly explain the equation used? If the fraction is more effective of shorter wavelengths, why does it spread out less? More effective means it diffracts it. You are right. So I guess I should say diffraction is less effective on shorter wavelengths. Honestly, I don't like just sentences you remember. If you figure out a sentence you can remember, which makes sense, use that. If not, just use maths, which is always better. So forget my little yeah.
Nina, we've all been there. I knew that. You're okay.
Just do the maths. Just do the maths. It's better. When is the equation W equals lambda times D over S useful? Let me write this down. So the question is, when is the equation W equals lambda times D over S? So is that angular frequency? And okay, you have to help me out and define W and D. So just please post another question. Okay, so a bunch of people are asking about derivation of this thing, which is understandable. So I'll go through it very quickly. Okay. So how I make sense of this is you have a slit, which is of size D. You have its middle point. You have some screen, which is a very long distance away. You have 2 rays, which come like this and like this. And here I say they form a minimum, okay? So what I'm interested in is the angle of this minimum, because this here is a very, very long distance. So L is way longer than D. This is D over 2 here. We can assume that this angle is equal to this angle is equal to this angle here, theta. Okay. What we do is we get a perpendicular here. Our goal is to find theta, right? So if we get a perpendicular here, something smart you can do is get theta in a little triangle where you know a bunch of things. So what we can see is that sinus theta equals this, which I'll call delta, and I'll explain in a bit, over d over 2. Delta is the difference in path of rays. So you can do this by projecting this ray onto this ray, but in my case, it's just easier geometrically to do it on the middle ray. So the difference in path length between this ray here and this ray here is delta. for a minimum, we want this delta to be equal to half a wavelength so that the two waves interfere destructively. So this is something useful to know. If you want destructive interference, you want the peak of one wave to coincide with the trough of another wave, right? So that the two cancel out. And this is why you need a path difference between the two of half a wavelength. So this would mean that this is lambda over d, which is the formula you guys gave me. So maybe the factor of 2 isn't there. Again, you can derive this a couple of different times, depends on your geometry, but the essence of the thing is that you get this relation, okay? Don't be too worried about like specific numerical factors in this sort of problem. If you need a numerical answer at the end of the problem, this is when you should be worried. But when you're just demonstrating like physical principles, that's fine. Derivation. Okay, I hope this is all right. You're gonna see it a bunch of more times, so you don't have to take it all in right now. But this is the basics. I'm gonna move on to the next one. And again, if you have questions, I'm gonna go back. And question 5. Question 5 shows a figure with 2 mirrors, a solid object, and has a bunch of questions regarding this. Again, even for myself, I would redraw this diagram just to see everything and to be able to figure things out. So we have X and Y. We have our solid object, and we have 2 points on this solid object called P and Q. So the first question is, an observer at A sees the image of P reflected in mirror Y and mark R. The position of this image. Okay, so in the first part of the question, notice we don't care about B and we don't care about Q, which is good for your diagrams. So don't overcomplicate your diagrams. So here we have an observer A who sees an image of P reflected in mirror Y. Very important not to mix up your mirrors. So how that works is obviously a ray will have to go to the mirror, get reflected, and get to our observer. These two angles are equal because we have a flat mirror. And the image, as usual, we extend the ray which goes to the observer. And we have a second ray, which is the one which goes perpendicular from the image and back. And then we extend this. And this is our image of P as seen by A. These two distances should be the same in principle. So this and this is the same. My diagram is bad, but that's okay. And the image, again, is virtual because those are continuations. Yeah, just information. But draw a ray diagram from P to the observer. Yeah, that's all they want from us. Then part B is, in which mirror would an observer at A see an image of spot Q? So because Q is on the side of this, it can't, like the furthest ray it can produce in the direction of A so that it can be reflected from Y is here. Like it can't have a ray going there, right? Which means the only image A will be able to observe is in X. Again, similar, oh my God, this is such a bad diagram, but I would submit this during an exam and I would be fine with this during an interview. So don't be, as long as your diagram is useful, that's fine. So this is the ray, this is the continuation you care about, which is the ray going towards the observer. And this is the other ray which goes down and up from the object. Continuation, and this is whatever they wanted to call it, S. Okay. Can you explain all the rays from the first part? I'm not sure which each one represents. All the arrays from the first part. So very quickly. This is the ray of photons, which goes from your object to the mirror and then gets reflected back and reaches the observer at A. This is a ray which goes from the image to the mirror and goes back into the image, so just a reflection. If you continue those two, you get your image. Yeah, I'm not sure what more to say about this. If the reflected ray from Q in mirror X would have the same angle, wouldn't it miss the observer at A? Would have the same angle. Oh, you mean, okay, so maybe my diagram isn't good enough. What I meant with this diagram is if you have your little box and you have Q and you have A and you have your mirror, you would look, yeah, this is a bit better. So those angles would be the same, and those angles here are meant to be the same. And there's always a ray which goes into A, because there's a ray which goes like this, and then like this, and then like this, but there's always a ray which gets reflected in this mirror and goes into the observer, okay? Is there times when angle of reflection is not equal to incidence? I can't think of one. If your medium changes in the middle, well, this is refraction already. Okay, Kat, if you think of an example, I think not.
No, I was thinking exactly the same thing, and I had the same thought process as you. I was like, maybe if the medium changed, and I was like, but then there's a second angle of
Yeah.
incidence.
Okay, I
So
think this is
yeah,
universal. I'm
yeah, I think
always
smell
afraid.
plot holds.
Yeah, I'm always afraid to make a universal statement just because who knows? But I think
Yeah,
this is safe to say.
as far as we know, yeah,
Yeah, as far as we know.
yeah.
How did you find the virtual image from Q to A? So if we look here, this is Q to A. Again, we always extend back the ray which goes into the observer. And then we always have a ray which goes perpendicular to the mirror. So these are the two things you need to build an image from a flat mirror. One ray which goes from the image to the observer and extend back the part which goes into the observer. And then one ray which goes perpendicular to the mirror, goes back into the object, and then extend this, and then you build your S point. How do we know the image is formed from the perpendicular ray from the object rather than a ray at any other angle coming from the object? Calvin, that's a very good question. It's one of those things. Okay, let me think for 1 second. Do all of those rays just come back to the same point? I think all of those rays, yeah, okay, that's the idea. Okay, so, sorry, I'm figuring things out.
No, I was just about to jump in, but I think you got there. As far as I know, we choose that one because it's the easiest one to draw.
Exactly.
But whichever rays you choose, because there will be a range of them, they would all converge on the same thing. Is that what you were coming to as well, Nina?
Yes, exactly,
Yeah.
exactly.
It's cool.
I'm sure there's a good way to explain why fundamentally this happens. But I can't right now on the spot. But anyway, oh, this is an actual, whichever ray you build, wherever it's going, it's always going to go back to the same point. And the thing is, if you have a perpendicular edge, it's very easy to draw this perpendicular to your mirror and then just continue it to find this point. Because otherwise you have to like do an angle. You could just take this angle, decide that this is 73 degrees, do another 73 and then continue it back, right? But you can work with 90. So
Yeah, I think we just choose the ones that are easier to
yeah,
use.
yeah, yeah,
I think, Nina, if you don't mind,
yeah.
I'm going to push us on this. I know there's still some questions coming through,
I
but
can
we'll share
type.
the recording tomorrow. You can type while they're doing.
Yes,
Shall
I can.
we move on and let Ken do his
Yes,
questions?
please. I'm sorry I took so long.
No, no, it's great. Thank you so much for going into loads of
Okay.
detail. I'm sure Ken will be able to jump in with that detail. So
Yeah.
I should
Thank
have my video on because I'm just
Yeah,
muttering in the
don't
background.
worry about that. That was great. I've had to relocate to my bed because the Wi-Fi is really bad and the Ethernet port is next to my bed. So I'm
You
just
are coming through much clearer than you were when you said hi to us
yeah.
earlier, Ken.
Um
Everyone, I would like to introduce you to Ken. Ken is one of our current undergraduate students, and he studies the elusive physics and philosophy course.
I
Over to you, Ken.
yeah, nice to meet everyone. I'm doing some pat presenting now, obviously. I'm on the whiteboard. This is my first time using a Zoom whiteboard properly. So I'm gonna does everyone see that?
I
Um,
can see you nice and clearly. Could you drop us a nice cheerful yes? Yep, we've got some yeses coming through in the chat as
okay,
well.
great. Okay.
Ken, before I disappear, do you need anything from me, or shall I do what I did with Nina and just disappear and jump in as needed?
Yeah, I think that would be great.
Great, cool, good
Thank you so
luck.
much. Great. Okay, so we're gonna do problems 6 to 9. Okay. Let me I think it might be easier if I just do a little copy and paste. I don't know if it supports this function, but I hope it does. Um okay, it doesn't. That's fine. I'll write the questions out. So we're on question 6 now. So a fisherman listens to the radio as he sits on the bank waiting for a fish to bite. The sound is also heard by the fish, and the path of the sound waves entering the water is shown in figure 5. I will draw figure 5 now. So we've got, oh, okay. So it's there. Got a little fish. Um, this is air. This is, I'll put W for water because writing is going so well. Here's our little normal. And then we can see that it bends away from the normal. Okay, cool. So describe what happens to the frequency. So we need to do the frequency, the wavelength, and the speed. Um, cool. Um, so Nina gave a lovely little heuristic for how to think of refraction and the speed. So it's the sort of car thing where if it's going faster, it'll tilt away, and if it goes slower, then it'll tilt towards. So as you can see in the diagram, it does. Yeah, heuristic is like sorry for everyone. Heuristic is literally just like a little trick that's not, I guess, not that like rigorous, but like really useful. Anyways, so it tilts away from the normal, as you can see here. So we know that the speed increases. Yay. Okay. So that's, yeah, it made me laugh too. So that's one part of part A. Sorry, I'm right next to a busy road. There's lots of ambulances. Anyways, so the next thing is what happens to the frequency and the wavelength. One thing that just remains the same when it changes is, sorry, when it goes from one medium to another, is the frequency remains the same. I think a nice way of thinking about this is that like right at the interface, the right at the surface, the radiation is coming in and like oscillating at a certain frequency, and it should be like continuous as it keeps going. So the frequency stays the same. And then finally, there's this. And then we can just figure this out very neatly by V equals F lambda. Tell me in the chat, by the way, if you think I'm going too slow or too fast. So speed increases, frequency stays constant. So to make this, make sense, then the wavelength must increase as well. Great. Okay, on to part B. I don't know how to move. Okay, there we are. Cool. So we're going to move down a little bit. Now we're on to part B. The Fishman radios has two speakers, as shown in figure 6. It's not a very informative figure. It's just that. Sketch a diagram illustrating how destructive interference between the sounds from the two speakers can occur when the radio is playing. A note of a single frequency, assuming that the waves from the two speakers start in phase. So I think just a nice, this is just a sketch a diagram thing. Because it's multiple choice, I imagine you just have to pick the diagram that looks the best, I think. I think Pat will tell me if I'm wrong.
Yeah, that sounds perfectly plausible, or potentially selecting from descriptions or things like that. But all the working that you're doing is still going to hold as valid.
Yeah, just to reiterate what Nina and Pat said earlier in the session, like do your working. It helps. A lot of the times if you're just doing it in your head, you make stupid mistakes, and you don't want to make a stupid mistake on the pad. So here you just want to draw a little diagram. I'm not a very good artist, but what you want to do and what you want to convey is that oh God, sorry.
You're fine. We can see, we know what you're doing. It's all good.
Thank you. Okay, so here, you just want to show, I mean, I think everyone knows if it's destructive interference, then the path difference is half a wavelength. So here you want to show that at this point, the wave from this part is, for example, at a peak, and the wave from this part is at a trough. Okay, cool. And then finally is part C. Part C, I think, is quite tricky. Part C, you can do it very rigorously and derive it, but I would say that is absolutely the wrong thing to do in this case because of the time pressure. I think in part C, you really do kind of have to sort of let your physical intuition and reasoning carry you through in this part. So part C is for a note of a single frequency and for a given separation of the two speakers, D. So we already know that. So here's one source, here's another. We know that this is going to be fixed, D. Okay. What must be the maximum wavelength and orientation of the radio for complete destructive interference to occur? I think so. The first thing I will say is that the first exam tip I said I just said, and the second exam tip I would say is that the people that write the PAT and the people that write these exams in general, they're all human, and sometimes, at least in my opinion, sometimes the questions are phrased in a slightly confusing way. And if that happens to you, like that's just life. You just have to try your best and try to suss out what they're trying to ask you. So here, like it says, what's the orientation of the radio? Obviously, they don't really want you to say, oh, the radio is lying on its side next to the river, because that's irrelevant to whether complete destructive interference occurs. I think probably what they want to know, or what they want you to answer, is the question of where the complete destructive interference happens, relative to how the radio is like positioned. Cool. And I think another nice thing about this is, so you want to find the maximum wavelength of destructive interference given the fixed distance. So I think, remember that if I write A, so A is the path difference, that has to be half a wavelength, for there to be destructive interference. And then if I just like draw like a little triangle, so here's one possibility, I guess. So the path difference would be sort of I use pink. This bit would be the path difference, right? If I draw another one like this, for example, and then a final one like, say, like all the way over here, like that. You can tell that generally, as you go sort of, sorry, I'm trying to change the color. As you go further right or left, so perpendicular to the orientation of the speakers, the path difference decreases. Because if you think about like the absolute limit, where you go all the way far to the complete right, then it'll look very similar to just two parallel lines. And in that case, there's very negligible path difference. So you can kind of suss out that the maximum path difference will occur when you're not going to the right or left at all, and you're literally on, I'll use orange, sort of this line. So if I take this point, say, so I'm using a lot of colors. If I take this point, it travels some distance, and the path distance is d. So we know that A, in this case, A is d. So we know that the maximum wavelength is going to be 2d. And we're going to say that the destructive interference occurs on this gold, orange, yellowish line. Cool. So I think hopefully that answers the question. It's not the most rigorous thing to do, but I hope that demonstrates that with the PAT, a lot of these questions you kind of really just have to use your intuition, use your reasoning. You can't just write down some equations and chug through the math. There's just simply not enough time for that. Cool. Okay. Sorry, I haven't been looking at the questions.
No, you're good. Don't worry. Somebody who just wanted a quick recap the answer, and someone who's a bit confused about the change in speed.
Yeah. Okay. Cool. So let me just do question 6. Let me scroll to question 6. Okay. Yeah. So question 6. So the sound waves they bend away from the normal. So that means that the speed increases. So so the speed would actually increase. In terms of what actually changed, the frequency stays the same, the speed increases, and the wavelength increases. What's the orientation? So this is question, this is part B. No, this is part C. The orientation, I think, is a slightly, I think, very, well, I say slightly, very unclear way of writing the question. I think what they want you to answer is where the destructive interference occurs relative to the loudspeakers. And I said along, if you can see the whiteboard, along the golden line. So along the line collinear with the line that passes through the two speakers. Cool. I hope that helped. Put more Q&A. I didn't quite get why we said 2D was the maximum wavelength. We said that 2D was the maximum wavelength. We didn't do it very rigorously, sadly, because that would take a very long time and use maths that you might not know. I was saying just from sort of a reasoning perspective, we want the wavelength to be maximum, right? So that means that we want the path difference to be maximum because destructive interference occurs at the path difference being half the wavelength. So the bigger the path difference is, the bigger the wavelength can be for destructive interference to occur. We said that the further right or left we moved, relative to how I'm drawing this on the whiteboard, the lower the path difference is. Because if you think about the absolute limit where you go all the way to the right, then the path difference is, very minimal. So it's sort of like if you think of like a triangle, the longer you make the two sides of the triangle, the more similar they become in terms of path difference. Cool. Great. I'm going to move on now because we're low on time. I'm sorry if I didn't explain that the best, but sadly we have some questions to get through.
No, we're all good. Remember, so you get on to your next question, Ken. I'll just remind everyone I'm going to share the recording tomorrow so you can have a look back through this. We will eventually share the solutions to all of the tutorials as well, but we're deliberately leaving it a bit late to make sure that everybody works through them before we share our solutions.
Cool. So question 7. So question 7a, to write a little 7. 7a, intensity decays as one moves further away from the source due to the rays diverging. If I is the intensity and r is the distance from the source, then I is proportional to r to the n for what value of n? So I is proportional to r to the n. Sorry if my handwriting is really bad. It is normally pretty bad, but it's not this bad. I think it's my Wi-Fi that's making my writing not great. Okay. So the straight answer is just n equals -2. This is inverse square. I think if you want to justify it a bit more, it's because when you have a source and it's emitting radiation and light, imagine that some of these arrows are coming out of the screen. They're not just different lengths for no reason. I'm trying to make it 3D. So the power that's being emitted is the same because it's just emitting radiation, right? The energies like per time is being the same. But here the radiation passes through a larger surface as it gets further away. And so, if you, with the aid of a little bit of dimensional analysis, we know that the units of intensity are watts per meter squared. We know that this stays the same because it's just the same radiation source. But we know that this increases. Well, the area that it passes through increases. So the surface area is 4 pi r squared. So the surface area is proportional to r squared. And so we know that then, let me just scroll down a little bit. We know that then because the power is the same, but it passes through a larger area, then we know that the intensity is inverse square. Cool. Great. Next part is just some dimensional analysis. So here we have part B. Rayleigh scattering is an effect that causes many optical phenomena. We can skip that first paragraph. If a beam of intensity I naught and wavelength lambda interacts with one of these particles, then the intensity of the light scattered is equal to, I'm going to write IF for final intensity. So I naught lambda to the m, r to the n, alpha to the 6, 1 plus cos squared theta. Okay, cool. So we want to find what m, n are because we want to know from dimensional analysis. Cool. So we already know that n is -2 from part A. So that gives us that. The next piece of information we use is that the final intensity has the same units of intensity, which of course is the same units as the initial intensity. So I'm just, these square brackets I'm writing to be like units of. So once you do that, multiplying things means that the dimensions just multiply. So this is equal to I naught times what's it, lambda to the m. . r to the n, alpha to the 6, and then 1 plus cos squared theta equals I naught. Then we can just do some algebra, cancel the dimensions of I naught on both sides, because we know that they're the same dimensions. This is going to be, so that's going to give us wavelength, so that's the m. Length, so that's length again. We know it's to the -2. And alpha, alpha is the diameter of the scattering particle, so alpha is the length as well, alpha to the 6. And we know that cosine squared and 1 is unitless. So we get this is equal to something unitless, equals 1. I'm just going to say 1 because we've cancelled out the I naughts. So that gives us m -2 plus 6 equals 0. That means m is -4. Cool. Feel free to ask me any questions if you do. If not, I'm going to keep moving on. Cool. Okay, and you can scroll as well. I didn't know that until very recently. Okay, we've got a very nice juicy, sorry, I'll wait for the Yeah, sorry about all the ambulances. Trust me, this is very annoying when you're trying to sleep. But it is what it is.
I can't hear them actually, Ken. They
Oh,
don't seem to be
really?
being picked up by your microphone.
Oh, wow. Whenever I'm calling
Yeah.
friends, they just can't hear
Ah,
me when the
no, it seems to be just annoying you, I'm afraid.
Oh, fair enough.
It's both
Okay.
good and bad. I'm sorry.
I should start calling my friends on Zoom. Um, that should help. Cool. Okay. A glass prism of refractive index n has a triangular cross section with, okay, so I'm just going to draw the diagram. As Nina said, literally, whenever you have a diagram, just draw it. It's really useful. So we have a triangle. Oh no. Oh no. My pen is not drawing.
Oh, wonder what's going on there. I can see the whiteboard, but obviously I don't want to draw on it.
Yeah, this is very strange. Um, yeah, I'm very annoyed about my Wi-Fi being very bad.
Do you want me
But
to make you co-host, Ken, and see if that gives you additional?
yeah, it might help, but I could also just create a new whiteboard. Let's see if that works. I go to no, huh?
See if that sorts you out.
I will be right back.
No, no, it's all good.
I'm gonna quit.
Because obviously you and I are technically collaborating on that. I could see it, but I was like, describing to me how to draw the diagram is an added level of difficulty that you do not want here.
Yeah, I think I need to work on my clarity of speaking already.
Yeah, it'd be one of those sort of team building challenges where everybody draws the same diagram and you compare.
And then it just gets worse and worse. Okay, let me see. Yeah, sorry for the technical difficulties. I think next
No,
time
we're all good.
if I'm doing this, I think I'll just I'll do what Nina did and see if I can do that.
There we are. I can see your whiteboard again. Don't worry about it. I think
Um,
actually, I'm just going to take this moment while you're sorting yourself out, Ken, to say to everyone, if you are ever in a situation like this where you're being asked to draw something on a whiteboard and your tech doesn't work, you just stay calm. All of us have been there. It's absolutely not a problem. And you can always find a workaround. So I'm sure Ken was about 30 seconds away from just writing it down on paper and holding it up to the camera. So I think sometimes we really fixate on there being a problem, but it's all good. And I like the stay calm. Excellent.
I just wanted to compliment what you
Yeah.
were saying.
Have I bought you enough time now? You good to go?
Yes, I'm great.
Excellent.
I think I don't know, maybe they just don't want me writing that much on whiteboards, so I'll just restart every now and then, I guess.
I am going to give you a 5-minute warning just to give you that notice, Ken. Don't worry
Yeah.
if you don't get through all the solutions because we absolutely are going to share written solutions to these in the end as well. So eventually everyone will have a complete set of solutions for all of the problems that we've done, as well as your lovely recordings.
Great. Okay, that works out. I'll probably just focus on this problem then. I don't think I'll try to rush over this problem and the next one. So this is problem
Perfect.
8. We're going to draw the diagram because that's the best thing to do. When in doubt, draw a diagram. So those are 45 degrees. That's right angle. So a glass prism of refractive index n. I'm just going to write n. Triangular cross section with two angles of 45 degrees. The prism floats on some mercury with the largest side of length L. So this is supposed to be an L facing downwards and a vertical depth of H. So I'm gonna put the fluid here. So there's a monochromatic beam of light entering the glass parallel. So I'm gonna do this in another color because I think it helps. Enters, it refracts. It totally internally reflects, and then it goes out again. And then I'm going to draw my little normal lines again. I'm just going to set this problem up because I don't think I'm going to have time to go through all of it, but that's okay. Yeah, that's not right. The normal should be on that side. Oh well. Okay. So, anyways, so you want to know the maximum height of the incident beam above the mercury surface such that the beam can leave on the other side of the prism parallel to the mercury surface. So if you think if it entered a bit higher, then it would go down here and then it wouldn't be able to leave. If it entered a bit lower, then it would, leave presumably like somewhere up here or something. So you want to know, so to solve this, you want to find sort of the critical point. And I think the critical point will be exactly when it goes down, it comes back up, and then it leaves literally at height h. So how you do this is when in doubt with these geometry things, literally draw as many triangles as you can. So the triangles here, we're going to name this x. So this is what we're solving for. That's what we want. And here we've got actually two very nice triangles. We've got this triangle right here. That triangle right here. It enters at it's got 45 degrees. It's got some angle alpha. And this angle here is going to be 90 degrees. Yeah, I hope England wins today, by the way. 90 degrees and yeah, but like Southgate does suck. No, I didn't say that. I'm very professional. And
Sorry,
plus,
Ken, I've totally thrown off your explanation. Carry on.
no worries. And theta r, so it enters at a angle of incidence I and goes through here at angle of its refraction r, right? And so that's a lovely triangle. We've got a height of h plus x. And we've got another similar triangle on the other side. So that's this triangle right here. Oh, God. That's going to be 45 degrees there, alpha here as well. And this is because it's leaving at the same angle, 90 plus theta r. So you've got theta r. What you can do is that you know that this length plus this length, so I'm going to call this C1, C2. We know that these lengths, C1 and C2, we know that that's going to add up to L, right? And we know we can figure out fine expressions for this length and this length via the triangles. and then we add them up to find C1 and C2. And then if you set everything equal to L, which I will do now, in the minute that I have left, you will find everything. I think. At least that's what happened when I did this before this. So we know that this, I'm going to call this A1. So A1, we're going to do some trigonometry. So we know that tan of 45, that's opposite over adjacent. So that's going to be h plus x over A1. We know that on the other side, so I'm going to call this B1. We know that tan of alpha is going to be h plus x over B1. I can rearrange for A1 and B1, and I should get something along the lines of, oh no, it's locked me out again. Ah. Okay. Well, it's locked me out again, but hopefully you can see that the strategy for these complicated geometry problems is draw as many triangles as you can. You know alpha because of Snell's law. You know the other ones, equate things that you know should add together, and then you will get X.
Perfect. Thank you so much, Ken. And finally, you've achieved the ambition of all students, which is you've left the rest as an exercise to the reader.
Yes.
The dreaded line in all physics textbooks. So guys, we are going to stop here today. We've reached 8 o'clock. Thank you so much, Ken. Thank you so much to Nina, who has already left us. And thank you to all of you who have attended today. We're aware that there's lots else on today. Don't worry for anything that we've missed. We are going to be sharing written solutions further on in the course. We're just being mean and making sure everybody really gives it a go without solutions before we share those with you. I'll share the recording tomorrow along with all of our notes and helpful links. And I'll share with you as well what we're going to be doing late over the summer. I'll see you again in person in September. Thank you so much, everyone. Goodbye for now. Bye, Ken.
Bye.